What's up, guys? How we doing? Just checking in here. We're gonna do a lesson here, but I just want to touch base with you kind of about the calendar. It is, just place to check is always kind of the Thermo unit. It's under Thermo unit plans in this Google Doc. So kind of the I went away from the kind of the daily attendance sheet. You might have one, but basically you get a lesson for every 2 days. It's kind of, I think, a little bit more manageable for people. So today we're going to learn about learning target 3, and then tomorrow if you want to finish it up or ask for extra help and so on and so forth, that's kind of the plan. And then Friday I'll have another lesson. So this calendar is kind of changing. I kind of change it as I go from week to week because I'm sure I won't stick to it, but at least for you, the week generally is what it's supposed to be. So that is that. Okay, so we're in our thermodynamics unit, and we're going to talk about this thing called Hess's law. Oh, one other thing. In the calendar, sometimes I will have videos, extra videos linked in there, and I can do that as well too, besides my lesson. If you're like, whoa, I need some extra help, that's that. But anyways, back to learning target. Uh, Use Hess's law to calculate the enthalpy of a reaction. Okay, so we started talking about what heat is, and if you remember back to, here's just kind of a review. Here's a chemical reaction, and we said the internal energy of a system is so H is enthalpy, uh, which is equal to the internal energy, which is Q plus W right here. That's work. But we said, hey, since we have an open system, that is negated. So the enthalpy is equal to the heat. All right. So basically, which is equal to the internal energy then. And that's kind of the gist. And there's just a lot of ways to calculate it. And this Hess's laws way is just a way for us to do it. So here's in a reaction. We want to calculate how much heat is given off in this reaction, and we're not quite sure. So it's hydrogen plus chlorine goes to hydrochloric acid gas, which we don't know the delta H for. We want to calculate it and figure out how much heat is given off. That'd be a very useful thing if you're about to perform this equation. So what we can do to determine H, there's 3 things you can do, 4 things. You can use values of their determined experimentally, so doing it in lab. All right, and that's what we would really do if we were in class. The other thing is calorimetry. That is learning target 5. We'll talk about that later. This is learning target 4, and then Hess's law is learning target 3. So we're going to talk about how to determine delta H. There's a lot of different ways to determine heat of a reaction, and that's one of them. So what is, let's get rid of this goofy thing. What is Hess's law? Its enthalpy is a state function. All right, so we talked about state being the final. We don't care about the in between. All we care about is the end, right? So a path function cares about how you got there, where a state function just says, hey, I got there. I went from point A to point B. Well, how'd you get there? Well, it doesn't matter as long as I get there. So many reactions take more than one step. So for example, in this reaction here, you have carbon plus oxygen goes to carbon dioxide, and carbon dioxide breaks down to carbon monoxide and goes to oxygen gas. All right, so there's just a lot of different chemical reactions. That would be the in between of the intermediates, you would say. Okay, so how do you do Hess's law? Well, Hess's law is this: you have an overall reaction, all right, and basically you need more than one reaction and multiply the reaction by the delta H. You can also use fractions. If you reverse the reaction, the sign becomes positive. All right, so if we want to figure out the enthalpy of a reaction, we can take a bunch of other reactions, manipulate it, and figure out, oh, here's what this will be based on these other reactions, essentially. So it's like putting together a puzzle. It's kind of fun once you get the hang of it. A lot of people like this because it just is a little bit of a process, and they can do it. So it just takes a couple of practice problems. You'll be good. Based on these, so we know these 2 reactions. These are tabulated delta H's. Now here's what we want to do. We want to get A plus B plus D. This is the reaction we care about. All right, we care about that one. We want to find the delta H. Well, the rules are this, okay? If I just take one atom at a time, or one compound, and I just want to make sure it's on the same side. So A is on the same side as A there. It's on the products reactant side. B is on the same side as B there. That one's good. Okay. but this P needs to be a product. So what I can do is I can say D plus C goes to P, and I flip it, and it makes it plus 18, all right? So now what I can say then is that reaction, I flipped it. What I want to do then is just make sure that the intermediates cancel each other out as well. So I got A on the left, A on the left, B on the left, B on the left. All right, I got C on the right and I got C on the left. Those are going to cancel out. That's good because you don't see it in our answer here. And then I got P on the left, and then I also got P on the right and D on the left. Okay, so everything does, and then all you have to do is add up the delta H's. So negative 25 plus 18, this becomes positive, right? And then that would make it for 7 minus 7 kilojoules. So what this is saying that this reaction that we just found is going to give off minus 7 kilojoules. Okay, so now let's actually do a problem. All right, so here's the actual reaction we don't know the enthalpy for. We want to find the delta H. Here are the intermediate reactions, all right, and we want to get it to look like this. All righty. So the first things first is you always just make sure, just pick one at a time. All right, so N2H4 liquid, that's on the left, that's on the left. All right, and I always like to circle if it's good. All right, O2 on the left. Okay, there's no O2 there, so that must mean somehow it's going to have to cancel out. N2, 4H2O. The other thing that you have to make sure you do is you have to make sure we get the right number on each for each number of molecules. We'll hang tight because right now I would guess that there's other waters that are going to help us there. Okay, so the next thing to do would be like, okay, well, H2 oxygen, all right, and then H2O, alrighty. Well, let's just see what happens here. So if I know that if I need 2 more H2Os, so that's going to make that, and I'm going to have, that means I doubled it, okay? So if you double it, you multiply the whole enthalpy thing times 2 of that intermediate. The other thing that I can see here is that we are going to have to get the oxygens to cancel out somehow. We'll just keep going. Okay, so I know so now I got 4. That's good. 4 H2Os on the right. That's good so far. The next thing I want to do is I want to look at H2O, HO2, and H2O2 here. So if I look at this here, I know H2O2 is on the left. Okay, so I got to flip this. So it's going to be H2O2 goes to H2 plus O2. Alrighty. So I flipped it, so that makes this sign positive. And then the other thing that I got to start making sure of is, okay, well, I have 2 of them. Where is it? So that is gone. Sweet. H2O2 is gone. Other thing is I got 2 of them here. So now I'm going to need 2 there. So it's going to double everything. So then that's going to be times 2. So it turns into positive when I flip it. And then I got to make sure I cancel everything out when I do that. All right. So now let's just go through and make sure we got everything. So I got NH4 liquid, NH4 liquid. Good. Okay. 2 H2O2s. 2 H2O2s. Good so far. All right. Now let's go to the product side. 1 nitrogen gas. Is it anything else cancel out? Nope. That's good. That one's good. 4 H2Os. So I got 2 there and I got 2 there. Okay, so that's 4 H2Os. So now I'm good. Whatever else is not in the equation better cancel out. So let's find that out. I got oxygen and oxygen. That's 2 of them. That cancels that one out. Okay, because that's on the product side. H2O, I got 2 H2Os. So what you're left with then is just everything that you need to be. All right. Now what I do then is I just add all these up, find the summation of that. Okay, so I got negative 18 or 818.2 kilojoules. All right, so that's the delta H for this reaction. So what I do in rehash, all I did was make sure the first thing you do is get the right reactants and products. If not, flip it. And then you got to start to cancel things out and make sure it matches the coefficients. Okay. And then if it does, whatever you multiply by the whole thing, then you got to multiply by this because this is the molar coefficient for, or the enthalpy coefficient for whatever, for 1 mole of what it is. Okay. Sweet. All right. So here's your worksheet. I will do a problem. I'll pause it and set it up, and then we can just check our answers. All right, so I just went to the answer key and copy and pasted instead of writing it all out. So let me just walk you through kind of what I did. The first thing that you got to just look for is just make sure that you get the right stuff on the right side. So C2H6. Well, that's on the right side here. That's on the left side there. So I'm going to flip this equation. So equation B here, I flipped. So this has got to get over onto this side. All right, and then what also I need to do is I need to multiply it by 2. If you can't tell, because there's 1 there, so then there. So I multiplied this by 2. All right, so and when I multiply it by 2, what I have here is, okay, I make it positive. So this goes positive, and I'm going to multiply that by 2. All right, so now I got that on the right side. The other thing that I need to do is figure out my oxygens. All right, so the other thing is if I look here, okay, well, C2H4, all right, is here. There's 2 of them. And then so I'm going to have to multiply this by 2 here. 2, that gets me to 6, 4, and 4. All right, so if you look, if I just multiply this by 2, it goes, like I said, 2, 6, 4, and 4. All right. So I just multiplied it by 2 because these need to cancel out. Now they do. They cancel out because it's not in my final equation. Big deal. So then I got oxygen on the left. You have 6, you got to get 7, so you're probably going to get an odd from somewhere else, all right? The next thing would be, and it's right here, all right? So that one got multiplied by 2, all righty? It stays, I didn't flip it, so it stays negative. And the last equation, I have hydrogen, H2, and in my original equation I got 1, a half, and it goes to water. All right, if you look here, I have 2 on the left, 2 on the right. There's no hydrogen here, so that's got to go. So how I do that is then I just multiply this by 2. Multiply a half by 2 gets to 1, and then 2 there. All right. So now what I have here is I have 2, that cancels that hydrogen out. I got my last oxygen for 7, and then I have 6, I need 6 total. Well, there's 4, and then there's 2. So let me just go through and double check. 2 C2H6s. Bingo, done. Okay, 7 H2O, O2s. Boom, boom, done. On the left side. So now I go to the right side. 4 CO2s. Bingo, done. 6 H2Os. There and there. Bingo, done. Add them all up. Okay, so make sure the signage is right. 2 times, that's that, plus that, plus that. And your answer is going to be, not sure. Looks like it should be right there, and it's not. But that's your answer. All right, go through the worksheet. Go ahead and try a couple. Just practice, takes about some time. Just in quick review, remember internal energy is delta U, okay, which is equal to Q plus W. Work is equal to negative pressure volume. We really don't care about that because that's only for closed systems. All right, heat is Q and enthalpy is H. Essentially what we can say is we can say the internal energy, delta U, is equal to the enthalpy because it's equal to Q because there's no work being done on the system because that's that. So that's essentially it. Why is this important? Here's the deal why it's important. You might be like, I don't really care. Well, because there are millions of compounds in the world that are countless ways we can combine them in chemical reactions. All right, it would take way too much time to do every conceivable reaction to calculate the heat that's going to be given off. Hess's law enables us to take already known heats of reactions and manipulate them to previous unknown reactions without having to do it. So, in summary, works because enthalpy is a state function. Doesn't matter if we use other equations. All that matters is we get there. All right, and add up the enthalpies. All right, guys. Let me know if you got any questions. You got today and tomorrow. Get it done.